All right. Beautiful spring day out there. Thank you for coming. This is, I think, even though we only get to spend a little bit of time on it because we're in these kind of last lectures where I'm trying to show you some of the vistas of control, right? But I would say this is probably one of the most important topics that we'll cover. And relative to its importance, I think controls doesn't have it nailed. I think there's still a lot of open problems in this space. So output feedback, you might call it these days pixels to torques. My volume's still high, right? Is trying to make decisions not just based on state estimation information or state information, but ultimately about directly making decisions from the outputs, from the observations. Okay, so let me say that in a few words. So far in class, we've been saying we have some state space equation. We started adding some W's in there, right? And then we're going to come up with a controller that, if we're doing well, maybe is even an optimal controller that's U as a function of X. Okay, today we want to generalize that in an essential way. Okay, so we still have xn plus 1 or x dot. Of course, all these things work in both discrete or continuous time. But now we're going to explicitly model our sensors, okay? In its full generality, it'll look something like this, where these are now sensor outputs. And this is measurement noise. And this, in my view, is a more complete model of a plant, right? I've kind of drawn this a few times, but I was always tempted to say y as some output, right? Because that's the real thing, is we want to have the command input. I could have put that maybe as one disturbance input, or I'll split it out just to be pedantic here about having W and V separated. Okay, and then I've got a signal going out, which is y, and you need to be able to compute y as a function of x and u. So if I have a multi-body system and I want to simulate a camera, for instance, then the information in x is enough for me to send my geometry to a geometry engine and have a simulated camera model my sensor. Right? So this could be a camera image. It could be the encoders I have on my links, right? It could be an IMU. All kinds of things are the real outputs of the plant. And then ultimately, we want to write a controller that takes y and outputs u. And the big question today is, how do we do that? Okay. And today I'll try to give you sort of the optimization and control view of it. And then next time we'll talk about the learning view of it. Okay? And I'll try to make those connections as we go. Okay, so when we are doing the state space control, the state feedback control, as opposed to output feedback. So the top one is state feedback, and then this one is designing an output feedback. Okay. In the state feedback case, we had this beautiful result from Bellman, or even before that, that the optimal controller is a static function. It's just a function of x, right? If you know x, then you just do a function of x to get u. Right? The optimal controller can be written in that form always. So the natural question then is how do we parameterize even, if we're going to search, these output feedback controllers, right? So a natural thing to try would be to write something like this, a static function. I'm just going to take my instantaneous observations, and I'm going to predict my actions from that. And that, when I look at it, I think of that as almost a straw man, because you can quickly come up with examples where that can't work. Like for example, if I have a problem where if I take the acrobat balancing at the top, we know that the optimal state feedback controller depends on both positions and velocities of both links. Let's say I only have encoders on my acrobat that give me positions but not velocities. It seems a lot to ask an optimal controller to work with just the position-only information and no velocities, right? Or if I took a picture of the acrobat and said, here's a static picture of the acrobat, decide if you should push left or push right. There's no notion of velocity that you can extract from one image. You could do it from multiple images, okay? So that seems like a tall order. It might be that it would need to be shown, but I suspect you could not design a controller of this form that would stabilize the acrobat from all initial conditions, maybe even the linearization of the acrobat. Right? Certainly you can come up with toy examples where that's true. But having said that, a lot of times you'll hear people say, in learning, they'll say, okay, well, the image is state, right? And that's like, well, okay, maybe that works, maybe that doesn't work. Typically, when people go to do it, they'll do a history of observations. Okay, so that'd be another natural choice. Maybe a fixed history of observations. Okay. Now this is actually a dynamic feedback. The term static here means it's memoryless. How did that go so wrong? Memoryless. Okay. And this one requires memory. I mean, it's a trivial memory, but somehow, since you only instantaneously, in the signals and systems picture, you only instantaneously have access to the current y's, you're going to have to push that into a memory buffer to remember the previous y's. And that is a representation of a dynamical system, a moving average kind of dynamical system. So that gets more interesting, okay? There's probably a bunch of other ideas that you might have come across or you might have. So another kind of idea would be what if I try to do state estimation? Right, I'm going to write one system that takes maybe histories of y's and estimates the state x, and then I'll use my full state feedback controller. Okay, that's another good idea. And there's a few more we'll go through, but I kind of want to just give the high level perspective here. And then maybe the most complete answer is if I give you the probability distribution over x, which is dependent on all of the previous observations and all of the previous actions. okay? This will be the belief space planning kind of idea, okay? So if I generalize my notion to estimating the state, to estimating an entire distribution over possible states, given everything I've seen a priori, okay, then this is going to be another one of our models. Potentially hard to work with, but we're going to see that this one is sufficient for optimal. Absolutely, you can make optimal decisions if you do this work. The question is just, can you afford to keep a representation like that around? If you are machine learning inclined, let's say, then I could have written a lot of this as sort of maybe I've got some latent state that comes from some encoder, okay? And people sometimes will encode into a latent state from a truncated history of observations. They will sometimes use a recurrent network or something, which might do something more like this. Okay, so I'll try to make some of those connections too. But you could think of this as a candidate for Z, some function of that. You could think of maybe this as a function of Z for Z also. Yes?
For idea 3 on the state estimate, is there also a variant where you would state estimate the entire trajectory, not just X hat in?
I totally understand the question. I think that the notion of a state is that it should be all the information you need to encode the past. And I think that the typical generalization, when having the mean of your state estimate is not enough, I think the more common generalization is to go this way. You could think of a history of this, but I think at some point you're better off thinking of it as working directly with those observations. Mm-hmm. So all of these, all of 2 through 4, they're all dynamic controllers, okay, in the sense that I want to shift this view from pi of x, static, with y coming in pi, to now being a dynamical system, u, that it has its own internal state. Maybe I'll call it x controller here, okay? And you can choose to parameterize it as an autoregressive model that takes functions of history of observations. You can choose to parameterize it in a state space model, okay? But what we want to do is sort of the big new thing that we have to deal with is that the optimal policy becomes dynamic controllers instead of static controllers, except for rare examples. Okay, so let's use a couple examples to sort of tell the story here. This is my hardware acrobat that we showed way back in the day, right? And a few of you asked, like, why is it not perfect at the top? This is the answer is because we're dealing with real sensors, okay? And we're dealing with stiction and backlash and the actuators, okay? So the dynamics of this change in important ways once you have to work with real sensors. I coded it up, of course. Okay, I'm going to do the thing where I don't show you my to-do list. You might ask yourself, why does he keep the URL of the server in his to-do list? But that's a complicated answer. Okay, oh, I forgot to run the example. Okay. All right, simple little thing. I set the real-time rate to be, I set it to be fast for making the plots, but okay, this is now stabilizing with a more reasonable model of the encoders, okay, and only using the encoder feedback, writing a state estimator, and then watching the convergence. And it's good, but it's not quite as good as the version without. So let's just look for a second about what that sort of looks like as a modeling paradigm. So my plant is the original Acrobat plant, okay, which is just the multi-body equations. I took in this example, I only added rotary encoders, okay, which I thought of as another dynamical system that I tacked on the end. It takes the full state and basically just throws away the velocities. It also does a little bit of work to quantize the outputs just to make it a little bit more realistic, okay? And then it produces an output port here, which is the measured joint positions only. I let the Acrobat state sneak out for visualization, but I don't use that for the controller, okay? And then I put that into an observer that we'll talk about. It's actually designed as a Kalman filter. And then I connect that through my LQR controller, which shows up as an affine system. And that's how I stabilize, okay? So this block plus this block together, this block, the Kalman filter, as we'll see, has state. It has the same number of state variables as my Acrobat plant. And then the LQR controller is a static map. But put together, they are a state space model that has both, that looks more like this. It has internal state. Okay, so we're going to have to lift up our thinking from searching over static functions to searching over dynamical systems. We'll work through that again when we get to that result. Okay. Similarly, when we talked about the quadrotor blowing around in the wind, I said we're going to not only need to estimate the state of the quadrotor, but also the state of the wind. Okay. Fine, we can do that, and we can put that state estimate into our feedback controller, and it will do pretty reasonable things. But that kind of model, this kind of model starts to break down when you start working with cameras, for instance, right? So this is just a super simple manipulation task, okay? But suddenly now the primary sensor in this is a camera, right? And the types of errors that we see in this are not Gaussian, okay? They become much more complicated. And this is where some of the machine learning tools have just really done incredibly well. All those are distracting. I'll put this up and we'll talk about it in a second. Okay, does that make sense? By the way, if I'm simulating that that system, then we have the multi-body plant. It has its outputs. We simulate that through an RGBD sensor, let's say. We treat that as our output Y, okay? For instance. And what's inside this. This is all the multi-body equations, right? Equations of motion, contact mechanics, all that stuff. Hiding inside this, it's easy to write a little box, draw it on the board, but that's like a rendering pipeline that tries to be performant and cache, right? So, and it's, even though people talk about differentiable renderers, this thing tends to be not a great thing to try to optimize through, right? Okay, so let's start taking through some of these ideas. So idea one is so tempting. Even in just, if you think through the derivations we've done, for instance, the sums of squares design for nonlinear controllers, polynomial controllers, it's be so natural to sort of stick in and search for polynomials that take this kind of a form. It's like the optimization software doesn't have to change very much at all, okay? But somehow it goes from something that works to something that doesn't work, okay? This problem turns out to be very bad. Bad in the way we already mentioned. One way that it's bad is that it's often not sufficient to make optimal decisions, you can make optimal decisions under this constraint, but it's often not sufficient to accomplish the task. But it's also bad in the sense that the optimization landscape is very bad. So finding optimal controllers in this class turns out to be hard. So let me say that. Even for linear systems. You would think this would be an easy problem. It turns out it's NP hard, which doesn't actually scare me away normally. I mean, I would say maybe the problems we actually care about, I mean, that says every problem in the class is, you know, or there exist problems in the class that are hard. And maybe the ones I care about are not hard. But even very simple examples turn out to be very ugly in this parameterization. So if I were to have this, you know, xn plus 1 equals axn plus b un, okay? This is sort of the canonical state space representation for an output system, you know, for my plant. And I just want to search over k such that, you know, find me a k such that, that I optimize, let's say, a LQR objective, something like that. When this was negative kx, we have all kinds of, we have LQR, we have all kinds of good results for solving that. Suddenly when it's negative ky, it's bad. Even though, even in the setting, I could make it so it's even just like this. You would think this would not be that much worse, right? Negative k c xn. Like, why should that be that much worse? But if c is not full rank, then this problem gets geometrically much worse. How do I say that? Well, okay, so here's a very simple system on the board here. This one came from Sasha Magretsky. He produced it out of his head during a conversation one time, and I recorded it for posterity. And it was one of the simplest examples I've seen of it. Okay, so yeah, so simple continuous time dynamics, just Cx. Just choose A and B like this. Okay, C like this. So now y and u are scalars. The state is got 3 elements. Okay. Controllers are scalar of the form negative ky, right? So I just have one parameter to search over, right? I can sweep k and look at every controller in this class, in this problem. And the question is, what does that controller do? And in general, right, forget about optimizing LQR. Let's just say, is it stable or is it unstable? The stability of this system, the closed loop system, is going to be A minus BKCX. So what matters is the closed loop eigenvalues of this system, right? I'd like the eigenvalues to be less than 0 for a continuous time system, for that to be stable, right? So this is just changing k around and asking what is the largest eigenvalue of the system. And it's just a simple illustration that in this particular case, there's some stabilizing controllers here. There's some other ones over here. And they're, you know, you can't get there from here, right? Roughly is so if you're doing, let's say, policy gradient, if you're doing gradient descent to try to search for the best controllers, this says, in order to get to a good controller that's hiding over here, you have to blow up your system, go unstable before you can go back. So it's a nasty optimization landscape if you're trying to walk around and explore controllers. You actually have to, you know, destroy your controller roughly to get back to the other good ones, or destroy your system. And this is a well-known result. So the optimization landscape for state feedback is non-convex, but it's connected. The set of stabilizing controllers is at least connected. You can always walk around in the set. You don't have to go unstable to get back. But for output feedback, suddenly the geometry changed. When C is low rank, it becomes a harder problem. So that's kind of interesting, right? So I think even though we know how to write optimizations that would kind of take this and try to search over K, they're going to be non-convex optimizations, and there seems very little hope of making them convex optimizations. Okay, and you're going to get stuck in local minima, things like this. Even ways that we kind of use nonlinear optimization, bilinear searches or other things tend to not perform super well in the static output feedback case. So roughly, don't do idea 1 unless you really have some good reason to. But idea 1 is dispreferred. Okay, idea 2 seems more promising, right? Let's do a history of observations. So something magical needs to happen to go, for this, if this is going to be good, which is going to be better, and this one's bad, then what happens, how many of these do I have to add before something changes? Like, why does something characteristically change in the landscape if I just start adding more y's? Okay. Now to see that, let's go actually jump up to the level of POMDPs. I think that's the cleanest way to see it. How many people know what a POMDP is? Okay, good, yeah. So this is, when we did the lecture on stochastic dynamics, we talked about having an initial probability distribution, let's say over x0 over x, and we talked about having our dynamics sort of function, which is like this, and then we actually talked about having a noise function like this, probability densities over x, over w, and then over the transition dynamics. Maybe this one depends on w too. Actually, no, that's good. Yeah. The POMDP just basically adds the observations on top of this. Now we also have some probability of y conditioned on, let's just say, on x, to keep it simple. Right, this is my observation probabilities. And maybe it's governed by some v like this. In the discrete time setting, discrete state, discrete actions, everything, then we know everything about this, okay? And it's actually pretty useful to think about it. So there's a couple like classical POMDP examples that people work through, and let's just think for a minute together about this one, okay? This is famously called the cheese maze. It's not a particularly complicated maze, okay? But apparently there's cheese in this block right here. And you have a robot mouse, let's say, that gets to move only one block at a time. The numbers are the observations. Okay? So the question is, if you're allowed to know the map, but you're not allowed to know your state, then if you wake up with some experimenter has set you down with uniform probability anywhere in the map, right? What do you do as a function of your observations to try to get to the reward at 7? Okay. So imagine you woke up and you see a 5. Right? Then you have a decision to make. You could be optimistic and just go for the gold, right? But there's a chance you'll see a 6, and then you haven't done sort of anything to disambiguate whether you're on this side or this side. You could be more conservative and go up, knowing you'll then see either a 1, 3, or a 4. You'll at least know where you are then, and then you can start making other actions. But to even remember where you are, you need to actually keep, like, to know I'm on this branch, and then walk through a 2 to get to the 3 and back down. You have to keep a history of not only the observations you've seen, but potentially what actions you've taken. Okay? So this is actually a very good exercise in thinking about what is the minimal memory that you need to accomplish the task from every initial condition. Right? So for instance, if you here you see a 2, right? Now you move to the right, you see a 3. If you only remember your history of observations, then you could get confused about where you came from, for instance, right? I guess that was maybe a bad way. Let's if it was 3 and I went this way, but is that a good one? Anyways, there's cases where you need to remember the actions you took in addition to the observations you've seen. Okay, so the right way to think about this, the sort of POMDP, maybe brute force way to think about this, is what I should maintain is a probability distribution over the entire map. So I'd think of it as a one-hot encoding, which says, what's the probability I'm in this cell, probability I'm in this cell, probability I'm in this cell for all the cells, okay? And then I'm going to update that based on my observations and the actions I take, right? So if it starts off uniform probability over here, then after one step, if I see a 5, then I suddenly have 1/3, 1/3, 1/3, okay? And I can maintain a vector of size 11, right, with real numbers that tell me the probability, and I can update them based on what I know about the map in order to shrink until I get probability 1 that I'm up here, for instance. Okay, and then I can make decisions based on that probability in order to accomplish the task. So that would take 11 numbers. This one, it turns out you can do in 7. I think 7's the best. But that's I'm not going to make you figure that out. But if you really try to pack it in and you only care about being optimal, not navigating everywhere, then I think you can do it in 7.
That's not important, but sort of funny to think about, like, what is the goldfish's space
Okay. Okay. I didn't see that one coming. So he said, yes. So something about mice having a long memory or goldfish having a short memory relative to an elephant having a long memory. Yeah.
So I guess, like, if you were to somehow be able to map out the space of the things that you do in the environment, like, how important is it to have a region like
Yeah. I haven't thought of it. Yeah. Why is a goldfish forgetful and an elephant have a long memory, besides having a bigger brain or something? I don't know. Yeah, that's a good one. Okay, does that basic idea sort of make sense, right? I'm gonna, maybe a sufficient thing for me to remember is a probability over where I could be in the space. And if I update that probability distribution after every action, then I can completely solve this task. It's not a minimal representation of a memory I need, but it's a sufficient one. So let me write that down now in POMDP language. I'll do it in discrete state and action version, okay? So if I said that BI at the nth step, this is the belief probability, is basically the probability conditioned on everything I've seen in the past. Oops, let's call it, I'll keep calling it Y for now here. So this belief distribution is this thing we're talking about maintaining, right? It's a probability distribution over the state space, okay, conditioned on my entire history of observations and actions. These are discrete actions. And these are discrete states. Okay. More generally, this belief is the output of an optimal Bayes filter. You've taken classes on state estimation, although apparently maybe there's not enough of those. It's the output of an optimal Bayes filter. Okay. So what can we say about this? So theorem, important theorem, even for output feedback problems, the optimal policy is a function of my belief state. Maybe it's a function of n too if it's a finite horizon thing. Okay. And the reason that's true is because it's a sufficient statistic. Okay, so if I call h of n my entire history from a0 an, y0 to yn, then the probability, my belief here, conditioned on that history and conditioned on this, is actually, it's sufficient to just use the belief. The way that the system is going to evolve into the future, if you know the belief distribution, then you know enough that you don't also need to carry around the history. Okay, that's also, I wrote it for the state, but that's true for every piece of the decision-making pipeline. If you know the belief, you know enough to do everything you need to do to move forward. It's a sufficient statistic of the past. Okay, so that's very beautiful. So one candidate, like I said, would be an 11-dimensional vector that just modulates the probability that I'm in each state, and I evolve that probability with an optimal Bayes filter. Okay, and then I can use that to make decisions. That gives me an 11-state model. It's sufficient, but it's not necessary. There's a smaller state representation that involves only 7 states that could have gotten the same optimal policy. So this is now a new picture that I want you to have in your head, kind of like this picture. So I'm saying we have y coming in, we have u coming out. I've got some particular x candidate here in my controller policy. Okay. One way to do this that we know is going to be sufficient would be to have an optimal Bayes filter. It has to put out an entire belief distribution, which in the continuous time case is a function over x probability, like the probabilities that we were moving around the van der Pol oscillator and the like. Okay, and then I can take this into a static feedback to get u. This optimal Bayes filter is going to have state. Okay. But if I can decompose my dynamic output feedback controller into this, I know that it can work. It's sufficient for making optimal decision making. The problem is that this can be hard to maintain. Like in general, it's a continuous function. We don't know ways to generally parameterize it, except for in special cases. Okay. But if you can parameterize it, then life is good. So we sort of bracketed the two solutions. Static output feedback is hard to search over and probably not, and there's no guarantees it's sufficient. It's likely it's not sufficient for many tasks. This is hard to represent, but definitely sufficient. The game of output feedback design is to, I'd say two things. One is to understand when you can perfectly represent this. There are some special cases. Tabular, linear, Gaussian, roughly. My playbook is simple, okay? So you can kind of understand how to solve this, right? And then there's a bunch of places where you have to only make approximations to this, okay? And I think the pressing question then is, how can we formulate a search whose objective is to do good control design that sort of searches for this representation? Call that Z, if you will. Compress that in a latent vector Z. What defines a good state representation for control? Okay, one place besides the discrete world where we can kind of write the POMDP. For small discrete problems, we can solve it exactly. The other place that it works out well is linear Gaussian control. In particular, linear quadratic Gaussian problems. Okay. In this case, if I have my linear dynamics, this is IID Gaussian. Mean 0. And this one is also mean 0 IID Gaussian. In that particular form, then we know how to perfectly represent the belief. We know that we shove Gaussians through linear systems. We only get Gaussians out. So a complete representation of the output of the Bayes filter is given by the mean and the covariance. okay? And I can take that in to my policy to get good control actions out. The optimal filter, the optimal Bayes filter for this is the Kalman filter. The Kalman filter is actually simple to derive, especially given what you've seen, because it has a Riccati equation that's almost identical to the LQR Riccati equation. There's in state estimation and control, there's a duality there, and basically everything you can do for estimation you can do for control, everything you can do for control you can do for estimation. One of the most popular ways to do state estimation in practice today is to actually do trajectory optimization backwards in time instead of trajectory optimization forwards in time. The Kalman filter is the optimal Bayes filter given you're working with linear Gaussian systems with mean zero. It can be discrete or continuous time. Yeah. If you run the equations, the optimal Bayes filter equations, for continuous, there's a continuous time Kalman filter, there's a discrete time, just like the LQR case. And in those settings, you just run the optimal Bayes filter equations, you get the Kalman filter equations out. Yes?
In the continuous case, are you adding to like x dot, you have like additive noise?
Yeah, it's additive noise, but it's from a white noise process. So you have to be a little careful. It's a Wiener process, and it's perfectly well defined, but it's a little harder to think about, maybe, depending on your, yeah. But you can write W as a function of T and carefully define how a Gaussian white noise process evolves. Mm-hmm. So this is like one of the cases that we can solve completely, right? And one thing we know is that if you have a linear control system and you have a state, you have a mean and a covariance of your current state distribution, this is actually stochastic LQR. If you remember, stochastic LQR gives you a controller that's exactly the same as LQR, but a cost to go function that it slowly accrues cost to infinity. So one of the biggest, most important results in control, certainly in output feedback control, is this LQG result. For the linear Gaussian problems, for the expected value of the sum over X transpose QX plus U transpose RU, the optimal filter is Kalman filter. Optimal policy is LQR. And you can separate the two. You can solve the LQR problem ignoring the fact that there's coming from state estimation, and you can solve the Kalman filter just thinking about the state estimation problem. And even more, LQR, even though we knew there was a covariance there, the LQR controller is not even going to use it. The optimal policy doesn't require knowing the covariance. So even though the complete characterization of the probability distribution involves the mean and the covariance, the optimal controller is not dependent on the covariance. The chain of argument work so far? Yeah? What you really want to do is carry around a probability distribution over your cheese maze or your state space, right? For LQG, we know how to do that exactly because it stays Gaussian. And it just happens for the LQG problem, the optimal policy doesn't even depend on the covariance. This is the separation principle. Of LQG. You can actually solve the state estimator separately of the Kalman filter. Now, one thing that happens all the time is for even nonlinear systems, people say, I'm going to build a state estimator. I'm going to write my full state policy that I'm going to design ignoring state estimation errors. And I'm only going to put the mean of the state distribution into my policy. Why? We don't know how, in general, like we know a lot about making policies that are a function of x, right? So it's easy to replace x with x hat. It's harder to know what to do with if you tell me I've got to give you a covariance too. But this is not optimal in general. In fact, it's not even clear if it's a particularly good choice, right? So the separation principle, which works for LQG, is a beautiful result, but it's kind of been abused by the world of control, where people build state estimators outputting only the mean and use that to make a static policy, a state feedback policy. But this can go arbitrarily poorly, right? You can imagine if my state distribution ends up being multimodal, right? Then making decisions based on the mean is like probably a really bad idea, right? It's true for LQR or LQG. It's not true in general. All right. So let's look a little bit more carefully at this example here. So I'm doing all of that in this little example here. So I have my Acrobat with encoder as a model. I have a couple things to visualize it here. Okay. I'm going to design a Kalman filter by taking my Acrobat with encoder and call a steady state Kalman filter to basically it's just like calling linear time, the LQR. You can pass in A, B, C. Actually, you only need A and C, right? And Q and R. Or you can pass in directly the system and it'll linearize for you, take your context. You also need to tell it W and V. And that'll give, just the same as LQR, this will give you your steady state Kalman filter. And that's the state estimator or observer, okay? And then, separately, I take the LQR controller and I only give it the Acrobat, nothing that knows anything about the filter, okay? And I wire it all together. I get that diagram I showed you, which is Acrobat with encoder, this observer, and the LQR controller, and the whole thing sort of works together. Okay? Even though this is a nonlinear system, again, you expect this to work sort of in the vicinity of the where the linearization is good, and then to perform badly both in its state estimate and its LQR controller and its separation assumption. All go wrong as you get farther and farther from that linearization. Yeah? And you can do this for the, I think you can pop in the planar quadrotor with the wind in this, and it'll just work. You'll see that if you plot the response of the undamped, or sorry, of the controller on full state feedback only versus the controller that has the state estimator in the loop, then one thing that definitely matters is that now this entire closed loop system, which is somehow my state estimate, my policy, my plant, okay? If I think of this thing as a dynamical system, and I want to estimate its region of attraction, for instance, call this my closed loop system. That closed loop system has now 8 state variables. It has the 4 state variables in here and the 4 state variables here. If you want to certify a region of attraction of the closed loop system, you have to do Lyapunov analysis on 8 variables, for instance. Okay, and that's it. You'll get important differences. This thing adds delay into the system, right? It takes time to reject noise. If you have noise, you have to sort of smooth that out. A causal filter that runs online will add delay to the system. So having decisions being made as the result of a state estimate is going to decrease your response time, change the dynamics of your convergence, and change your ROA. Okay? Yes? It's enough. This is a state space model. So this, you could write this as xn plus 1 is ax n plus bu. And inside here, y equals cx. In here, there's a state space form of this. There's a state space form of this. If you want to write the diagram, if you just ask Drake, what is this controller, or what does this system look like? It'll tell you it has 8 state variables, and the dynamics are going to be this block form where you have the dynamics of your estimator, the dynamics of your plant, and a few terms that couple them. Yeah. So now you just have a bigger system. You ask your Lyapunov function, is this bigger system with 8 states stable? And that is equivalent to where does the delay come from? That comes from the dynamics of the 4 states that go here. Right? Does that make sense? Yeah, that's right. It blows up the number of states, but doesn't fundamentally change it. There's a bunch of other things we can throw in that to make that more approximate. So I already did the quantization errors. The real acrobats have calibration offset errors, like you didn't know where 0 was. And so imagine, so if you're trying to balance a quadrotor or an acrobat, right, and you don't know exactly where 0 is, that's really bad because now you think this is 0, right? You're going to try to fight back, but you were actually there, so you're going to push over here, right? Very, very small calibration errors lead to this kind of oscillating behavior. The quantization errors do matter, even though we have encoders that have lots and lots of ticks. They do add up because you're trying to be exactly here, but you don't actually know if you're there until you move over by 1/100th of a degree, and that's enough to start move you away from the fixed point, right? And then the backlash and the stiction are the really big ones for that. I don't, so maybe the fundamental question there is, can clever mechanical design get around these problems? I mean, I think control is all about balancing unstable systems, right? I think that if you can make the system passively mechanically stable, then it'll be easier to control for sure. But I think you're going to find problems where you just can't do that. You want to use a controller to fight that instability. Yeah, I don't think you can design your way around everything about that. Yeah. Mm-hmm. Yeah, for sure. So now, this is it was good to make me write this, right? So maybe the general way to write this, if I have now xn plus 1 is ax. I'll shorten my notation a little bit over here. Y equals cx. Maybe I'll write this as the controller one, little subscript c's over here, just to have them different. If I wanted to think about this as a joint optimization problem, right? I said we're going to try to lift our thinking from thinking about what is the, searching for static controllers to searching for dynamic controllers. If we say I have A, B, and C, and I want to search for AC, BC, and CC, can I write an optimization problem that searches over A, C, B, C, and CC that will solve like a least squares problem? And it's very surprising, until you look into the details, that this problem has a nice solution. It can be written as a semi-definite program, as a beautiful solution, when the state dimension is the state of my controller is the same as the state of the plant, or bigger. As soon as the dimension of my controller gets one smaller than the state of the plant, everything goes to hell. The problem becomes non-convex. There's a rank constraint that's always there that is trivially satisfied in the optimization and can be discarded when the state dimension is large enough. And the optimization problem gets harder once that gets smaller. Okay? So optimizing output feedback policies, the rule of thumb is, yes, we can do it for linear systems, and there's nonlinear extensions, if your state is the same size as the plant state. Okay, philosophical soapbox here. Okay, so we shouldn't do that. I think for humanoids we maybe should do that, but for laundry folding robots we should not do that. And I think even for humanoids we probably shouldn't do that. Okay, so what this is roughly saying is that I need to estimate the full state of the world in order to make control decisions. Okay, and I have my 5 examples or whatever, but if I'm going to button my shirt, and I have a pretty good little simple feedback controller like this, okay, that sort of just feels where my button is, maybe looks around a little bit, I should not have to start by estimating the full state of my shirt. Like there's an infinite dimensional, something going on in the back there, right? That should not be a requirement for making optimal decisions. Unfortunately, most of our tools from optimization get stuck on that because the optimization landscape changes. So I think as a result, although there are some results I'll try to sort of mention, I would say control has not done an aggressive enough job tracking down when that works in the reduced order setting. Okay? There's an important problem called reduced order LQG that tries to estimate a subset of that, and a little bit is known about that, but not a lot. Okay, so it's sort of a surprising gap in the control world. Does that make sense? Okay. This isn't still quite the right problem. Right? I think it's an interesting problem, a good problem, but still I think a poor representation of what's happening in machine learning today. Okay, reduced order LQG would be find me a dynamic controller find A, B, C, possibly D, those, to minimize the expected value of the LQR kind of cost. Okay, where dimension of XC is less than, strictly less than the dimension of X in my plant. And it's surprisingly difficult. I'd say one of the best ways we have to do this right now is it falls under the umbrella of disturbance-based feedback. Or system-level synthesis. Which effectively unrolls the dynamics in time, solves a big kind of MPC kind of problem where you're actually searching for AC, BC, and CC. You can parameterize it in this disturbance feedback way, in a particularly clever way that makes that convex. And you can get a finite horizon version of this problem with reduced state as a convex optimization. Okay, and then you can say, as that history gets long enough, maybe it approximates the infinite horizon case and gives me the solution I really want. But there's something not quite lovely about that. It seems like, you know, right now the problem gets harder and harder and harder as you make the horizon longer, and we should have like an elegant infinite horizon solution, and it doesn't right now. It truncates. Maybe you can make some claims, but it's not a beautiful solution. But there's sort of like a surprising lack of algorithms in this space. Another approach would be, let's say, to do sums of squares kind of alternations. So which is kind of a non-convex optimization, particular form of non-convex optimization. You don't need sums of squares in the linear case, but the decay alternations I didn't introduce. So there's a version of sums of squares that simplifies to something pretty reasonable in the linear case. And you can get pretty non-trivial solutions from this. This is just an example of Glenn's recent work doing reduced order visual motor policies, where he's taking camera as input, using a key point detector to make kinematics of his quadrotor as the observations, okay? And then doing sums of squares kind of optimization to find reduced order stabilizing controllers in that. So there are examples in the literature of doing that kind of thing. But I have to say they're being absolutely crushed right now by the learning approaches that we'll talk about more next time. Okay, so I wish there was a happier ending to that, but I do think I think the theory of what's happening in these models that we're gonna, when we look at the learning-based versions, where I think we'll lean back into this notion of a belief state and a notion of a dynamic controller, and how it's represented either as a history of observations or as a state-space model like a recurrent network. Okay, I think all of that's going to make sense in the context of what we talked about today. But I do think that the results we have, the practical results we have in output feedback that we want to run on real robots are a little disappointing. I mean, state estimation works great for many cases, but for like folding laundry, it's not going to get the job done. Yeah. Okay, so I think that's the natural time to transition, and I'll pick up the rest on Tuesday.